One, and welcome everyone to another Zoom for Thought. This week we have Adu speaking to us about spooky groups and the general Burnside problem. Take it away.
Well, thanks for inviting me and sweetening the incentives enough to get me to talk. And thanks again to Ryan for letting me borrow his iPad for this. Okay, but yeah, let's start. So yeah, we're gonna talk about the general Burnside problem, which if you read the abstract, it's this problem. So G is gonna be a finitely generated group and every element of G has finite order. So not just that like every element in the generating set has finite order, like every single element in G has finite order. And the question is G finite? And so if you read the abstract, you know the answer is yes. But if this condition, so if G is like a subgroup of the general linear group and K is a field, and so this is true. I mean, Schur proved it when the characteristic of K is 0, and then Kaplinsky proved it for any field. Right. Oh, I should also shout out that I think, other than Burnside, Kaplinsky is the only mathematician I'm going to mention in this talk who's not Russian. So thanks to Kaplinsky for the diversity. Yeah. So yeah, this is nice. And also like this G is a subgroup of GL and K seems like a kind of stringent condition, but this actually like gets a lot of groups out of the way. So like for like every finite group is a subgroup of GL and K for some n. Every free group, every countable free group is a subgroup of GL and K for some n. All right. So this is a pretty good result. But the answer is no in general. So yeah, we're going to do a counterexample. We're not going to do the original one, the Golod-Shafarevich one, but that was the first one. All right. And so we're going to start with this thing, the infinite binary tree. Okay, so yeah, it starts at the top, and then, dang it, branches left and right, and then at every node branches again, right? And so we can label the vertices. Okay, so it's going to be all finite binary sequences. Okay, so right, we could label this one like 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, so on. Yeah, and we can label the top one empty set too, just so it's consistent. All right. Really quick, maybe pause the recording again if you want. All right. Oh my God, Ryan. Yeah, vertices are all finite binary sequences, right? And then you could just kind of see that two sequences would
I'm
have
sorry,
an edge.
I've forgotten what a group is. Could you read?
We don't need any groups yet, man. These
okay, very nice.
Just need combinatorics and graph theory.
Okay, I'm gonna leave now.
Yeah, so like any two vertices would have an edge if you could get from one by just deleting the last thing in the sequence, right? Like if you deleted the 0 here, you get that 0, so there's an edge. And so on. Wait, oh, I need to do this from the iPad. That edge. Cool. That was sick. All right. Yeah. And now let's talk about automorphisms of T a little. So like a graph automorphism, just a bijection between the vertices that preserve edge relations, right? And so right away, right, if gamma is an automorphism, right? And we're going to need gamma of empty set to be the empty set. Right. And this is for the simple reason that the empty set has 2 edges coming out of it, and every other vertex has 3 edges coming out of it. Right. And then because of this, right, gamma of 0 is going to need to be 0 or 1 because it's connected to empty set. And gamma of 1 is needed to be the other one. Right. And so like one valid automorphism is you just take the whole left subtree and the whole right subtree and just swap them. And then the last observation is that T has many subtrees that are isomorphic to it. Namely, if we just like picked some vertex, say 1, and then looked at the whole subtree under it, that thing's going to be isomorphic to T because it looks the same. All right, and so now let's talk about a couple distinguished automorphisms. So there's this one A here, which I already mentioned, and I drew it like this. But pretty much what I mean by this triangle here is that this is a subtree isomorphic to T, and this is a subtree isomorphic to T, and we're just going to swap them. So this one just swaps the 0 subtree with the 1 subtree. Right. And so like inwards, A just switches. That is not how you spell switches. Right. A switches the first digit of any sequence. Right. And now we got a little bit 3 kind of crazier ones. Right. So it's the same like pictorial idea. Right. B here, it's just going to swap these 2 subtrees, and then also these 2 subtrees, and it's going to fix that one and swap these 2. Right. So like one is like how you could view B is like, say, look at this one. Right. If your first digit is a 0, and then it's going to swap whatever the second digit is. And then if your first digit's a 1, your second digit's a 0, it's going to swap whatever the third digit is. Right. That's how to think of it. And so, yeah, we have these 3. And they look kind of similar, right? B swaps like the first 2 out of every 3. C swaps the first and third out of every 3. And then D swaps the second 3 or second 2 out of every 3. And so quick observations, right? All of these are order 2 because you just swap and then you swap back. And then also, say we did like B then C. Right. So that's going to fix the first one. Let me do it in highlighter. Right. This one and this one together will fix that first subtree. This one and this one will swap the second, and this one will swap the third. Right, and that's exactly what D does. Fix the first, swap the second, swap the third. So BC equals D, and this is also CB. Right, and then also by the same like idea, BD is C, which is DB, and CD is B, which is DC. Right. And so if you just look at these, then you instantly get that the subgroup generated by BCD is isomorphic to Klein 4. Cool. So yeah, any questions so far? All right, sick. Okay, so yeah, we're going to define the Gregorchik group. And so it's just going to be generated by A, B, C, and D. And the claim is that this is going to be our counterexample to the Burnside problem. So we're going to show that. All right, and so right away, we can like think of how we're going to view these elements. And so we can write any gamma as, let me just write it as this. Right. So I'll explain all this in a second. So we have A to the epsilon 1, and then there's like G1A, G2A, dot, Gn, and then A to the epsilon 2. Epsilon 1 and epsilon 2 are in 0, 1, and all the Gi are in BCD. And the idea here is it's just using these rules. So anytime we have a word in like B, C, and D, we can just concatenate those to like one letter that might also just be identity. And then all the A's are order 2, so anytime there's 2 A's, they just put together to be identity. Right, and so then you get this. So yeah, questions again? Okay, and yeah, the claim is that this is our counterexample. And so right away we have that it's definitely finitely generated. And we just got to show it's infinite, and then every element has finite order. Okay, and so first we're going to define this subgroup. All right, so this is the stabilizer of 1 in gamma. So it's pretty much all the automorphisms that fix that vertex 1. Right, and to recall, 1 is just this vertex here. Okay. Right. And then quick note, right? If gamma is in the stabilizer, then it also has to fix 0. Right. Because it fixes 1, and 0 and 1 can have to be after 0 and 1, so also 0 has to map to 0. And then another note is that if gamma is in gamma, right, then we're going to have gamma in the subgroup if and only if gamma can be written using an even number of A's. Right, and so to see why this is true, we just had to go back and look at these pictures a little. Right, so A definitely swaps 0 and 1, for sure. But then B fixes 0 and 1, C fixes 0 and 1, and D fixes 0 and 1. Right, so when we're writing these in terms of A, B, C, and D, the only way that 0 and 1 are going to be fixed is if we have evenly many A's. So yeah, questions again? We're still good so far. Sick. Okay. And so we're going to define this group homomorphism from this subgroup to gamma. Right, and so first, we'll do it in words. Right, so if gamma is in this subgroup, right, then gamma is going to restrict so it's restricting automorphism of the subtree starting with 1, right? Because it fixes 1, and so that whole subtree is going to descend to itself. Right? And so now, this subtree is isomorphic to T. Right? And so through this isomorphism, so pretty much like apply gamma restricted to, I didn't really have notation for this, the subtree to all of T under this isomorphism. And so I'll do examples of this too, in case it's not super clear. But oh yeah, just as a reminder, this is the subtree starting with 1, just that right one. And so yeah, let's just do examples. So if we do B, right? So the subtree starting at 1 is everything here. Right? And so phi of B, it's just going to say, just look at everything here and pretend like it's the whole tree pretty much. So phi of B is this thing, and this thing, if you call, is exactly C. Does that make sense? Or questions? Cool. Right, and then same thing, C, look at this thing, and that's D. D, look at that thing there, that gives you B. All right, and now last thing is, if you do ABA, if you just play with a little, you'll realize it looks like this. It doesn't take that much work. And now when you look at phi of ABA, that's just this thing, which is A. And so then right away we see that A, B, C, and D are all in the image of phi. And what does that mean? It means that phi is surjective. Because it has all the generators in the image. And corollary to that is that gamma is infinite, right? Because gamma is surjected on by a proper subgroup. Right. This is just a statement about sets now, pretty much. you can't have a finite set that's projected onto by a smaller subset. And so there's no way gamma could be finite. So yeah, I like that. I think that's a pretty good way to prove something's infinite. I'm a big fan. Yeah, let me ask questions again. Oh wow, 10 out of 10 from Scotty. Sick. Okay, and now his theorem. Oh, we have some chat messages. Oh yeah.
It's mostly memes. Forget it.
Oh, I just saw the most recent one, and it was great. Okay, and now I want to show everything as finite order. And so, in fact, we're going to show that the order is a power of 2 for every element. So we're going to let the length of gamma be I should say shortest. I'll say representation. But don't mean that in the sense of representation theory yet. All right, so just like every gamma is a word in A, B, C, and D, and so let the length be the shortest word that you can define gamma with. So like e.g., the length of AB is 2. All right, and now we're just going to induct on the length of gamma. Okay, so a couple base cases are easy. Length of gamma is 0. Gives you that gamma is 1. Right, so that's finite order. Length of gamma is 1. Gives you that gamma is one of the letters. All right, and that gives you that gamma squared is 1. So a couple base cases. And now, suppose it's true, like for the induction hypothesis, that if length of gamma is less than or equal to k minus 1, then gamma has order of power of 2. Okay, so pretty much there's 2 cases here, and we're just going to do one of them. So case 1, k is odd. Right. So if k is odd, right, we can write gamma as a to the epsilon 1 g1 a dot 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 gn a to the epsilon 2, right? And we're going to suppose this is shortest length. Okay, and then the key observation here is that what's on the inside here, right? So this has like n g's and then an a between all the g's. And so this thing on the inside is odd length. Or it's an odd number of terms. I shouldn't say odd length. Right. Just because there's n g's and an a between each g. Okay. And so because that's an odd number of terms, we need the whole thing to be odd, right? Which gives you that epsilon 1 equals epsilon 2. Remember that epsilon 1 and epsilon 2 are either 0 or 1. Right? And so either there needs to be an a on both sides or no a's at all. Okay. So if epsilon 1 is equal to 1, right, now there's an a on both sides, and gamma is conjugate to a gamma a, right? Because a is its own inverse, and then that a is just going to kill the a's on both sides. So this is a word. Length k minus 2, right? Because it killed the a on both sides. And then if epsilon 1 is equal to 0, right? So now there are no A's on the outside, and gamma is conjugate to, this will do G1 gamma G1. Right, and so what's going to happen here? The G1 is order 2 because it's in B, C, or D, right? And so it's going to kill the G1 on the left. And then Gn times G1, that's either going to be identity or it's going to be another one of B, C, D, right? So this thing has length, right? This is a word. Right, it's going to be K minus 1 if G1 doesn't equal Gn, or K minus 2 if it does. But either way, it's less than K. Right, and so there we have it. In either case, gamma is conjugate to something which has order of power 2. So gamma has order of power 2. Okay, and then won't do even case. Not gonna lie, the even case is like way harder, but it's not that hard. The even case, you split it into 5 more sub cases, and then you attack each one. Okay, but so yeah, if there was like some details so far that you weren't 100% on, I wouldn't worry about it too much because we're not going to need any details other than the fact that the Burnside problem isn't true from now on. Right, so we're going to let G be just any counterexample to the Burnside problem. So G is infinite, finitely generated, and every element has finite order. Right, and then recall that result by Sharon Kaplansky that G can't be a subgroup of GLNK for any K. Right, and so what you get is that if you have any HOM from G to GLNK, then this HOM has to have finite image. Right, because it cannot, like pretty much any homomorphic image of one of these groups, like any homomorphic image of a finitely generated group is finitely generated, and any homomorphic image of a torsion group is torsion, right? And so its image couldn't be infinite then because it's a subgroup of GLNK. It's got to be finite, right? And so this is pretty cool then, because what this tells you is that any representation of G over any field is determined by a representation of a finite quotient of G. And by representation, I meant finite dim. Right. And this is like, oh, first off, this is crazy for 2 reasons. Finite dimensional representation theory, or representations of finite groups, is in general a lot easier to study than infinite groups because you have nice things like characters. And so pretty much as long as you understand all the finite quotients of G, then you can just attack its representations using representation theory of finite groups. Also, I don't know that much representation theory yet, but like when you're studying representations of a specific group, at least from my experience so far, it's always very like field dependent. So you always get results where it's like this holds if K is algebraically closed to characteristic 0. This holds if K is like literally just the complex numbers or something like that. But in this case, it works over just any field, which is pretty good.
How well do you actually understand the finite quotients though? Isn't that just kind of...
Yeah, so that depends a lot.
Is that actually easier? It seems like you're just kicking the can down the road.
It depends what G is, right? So here G is any counterexample. So like for one counterexample that I'm about to talk about, we understand the finite quotient pretty well. Okay, so this definition. So let P be a fixed prime, and we're going to find what's called a P-Tarski monster. And it's an infinite group G satisfying that any non-trivial subgroup has order P. Right. And so maybe your first question is, do these things exist? And that's a very valid first question, but we're going to kick it down the road a bit. And so let's talk. I mean, does anyone have any questions on the definition first? Let me say that.
So do there exist? It's fine if we don't construct one, but do there exist something that actually does this?
Yeah, well, we'll get to that.
Okay.
Okay, but first, yeah, properties if they exist. So G is a P-Tarski monster, and property is that it's a counterexample to the Burnside problem. So it's infinite by definition. And so I'm going to say that if X is any element G, then X to the P is 1. Right? And this is just because X is a subgroup, or the subgroup generated by X is a subgroup. It can't be the whole thing, because that would mean that G is isomorphic to Z, and Z does not satisfy this. Right? And so that means the size of X is either P or 1, right? Which means X to the P is 1. And also G is finitely generated. So pretty much also a nice proof, right? Let X be anything that's not the identity, and Y be anything that's not in the subgroup generated by X. Right? Now XY, this subgroup, its size is greater than P, because it has the subgroup generated by X and it also has Y. So XY is equal to G. Yeah, I mean, maybe like once you see some of these proofs, you get even more of a flavor for how ridiculous these groups are, that like things like this work out. Also, G is simple if it didn't have enough nice properties. So let N be a normal subgroup of G. Non-trivial. Okay, and let H be any subgroup. Non-trivial. And also not equal to N. All right, so N is normal, which means that Hn is a subgroup. Right, and when N is normal, you have that like the size of Hn is the size of H times the size of N when they don't intersect. Right, and so this is a subgroup of order P squared. But that can't happen because every subgroup is order P. So I get questions on this proof. Make sense?
Even so, wait, there could be a normal subgroup. What happens if there's a normal subgroup, but there's no other subgroup, I guess?
Oh, yeah. So if there was no, I mean, that can't happen pretty much because choose any X out that's not in N.
Sure, yeah, good point. Good point.
Mm-hmm. Cool. All right, and now the big question is, do they exist? And this nice theorem by QuestionsComments says that if P is greater than 10 to the 75th power, then P-Tarski monsters exist. Pretty good. And actually, same theorem, but I wanted to split it up for shock factor. If P is greater than 10 to the 75, there are uncountably many non-isomorphic ones. So yeah, there's your shock factor. But yeah, I thought about doing my talk about just constructing these, but it was too hard. I found a book and it was like chapter 25 in that book, and that chapter frequently referenced earlier chapters. And yeah, these are really good for counterexamples in group theory in general. So they give you a counterexample to the general Burnside problem. They were actually constructed as a counterexample to the von Neumann conjecture, which that one says that any non-amenable group has a free subgroup, and this is a non-amenable group without a free subgroup. It's actually like, it's also a counterexample to the slightly stronger version of the Burnside conjecture called the bounded Burnside conjecture, right? Because if you notice, like with the Grigorchik group, like everything had finite order, but it was not the same finite order, whereas everything here has the same finite order. Right? This is a group, a finitely generated group of exponent p, which is much stronger. That's infinite. All right. So yeah, these are sick. They're awesome. And now let's just like put some results together. So let's look at representations of a Tarski monster. And so when I just say Tarski,
Can I ask a question?
yeah.
How about p less than 10 to the 75?
I was
Oh,
gonna ask how is this sharp?
Like,
I was hoping
uh,
that was gonna be the big
do
question.
do none of these just work?
No. Well, I don't know actually.
Huh.
So there are no 2 Tarski monsters.
Okay.
There are no 3 Tarski monsters. And I think the existence of a 5 Tarski monster is an open problem.
Okay, great.
I think. I guess I know that it is not known that there is a 5 Tarski monster. It might be known that there isn't a 5 Tarski monster, but it might be open.
Gotcha. Much appreciated.
And I think it's open.
Fantastic.
Okay. Yeah, and I don't know about numbers bigger than 5 and smaller than 10 to the 75th.
For
Yeah,
this
so,
or
like-
in general?
Yeah.
Yeah, like, I mean, I was adding on like Locky for reference. I mean, you can just take the presentation of the group, right? It's like you have like finally many generators, all of order 5, and basically no other relations. And you ask, is that group does that have to be finite or not, or something like this?
Yeah. So that question is open.
Right.
Yeah.
That's like very similar to this.
Yeah. So that like if there was a 5 Tarski monster, that would instantly solve that question.
Right.
I know there's
Yeah.
not known to be a 5 Tarski monster, but it might be known that there just isn't a 5 Tarski monster.
Okay, that's a helpful way of thinking about it. Thanks.
Okay. Yeah. So last thing, let G just be any Tarski monster. So here I just don't care what P is, just P Tarski monster for some P. So since G is a counterexample to the Burnside problem, any HOM has finite image, right? Since G is simple, any non-trivial HOM has to be injective because its kernel has to be a normal subgroup. Right? And the conclusion is that any HOM right? It can't be injective in a finite image if it's infinite. Right? And so what this means, right, is that all finite dim reps of G are trivial. Over any field. It's pretty nuts. And yeah, I think that's a good showstopper at the end, hopefully. So I'll call it there.
Well, let us thank the speaker. Anyone have any questions or comments about these fake groups?
Yeah, I have a comment actually.
Yeah.
So one of the interesting properties of these Tarski, so one of the counterexamples that they give in group theory, they actually provide a counterexample to, I think it was von Neumann's conjecture.
Yeah, I mentioned that earlier.
Oh, you did, okay.
Yeah, an amenable group without a free subgroup.
Yeah, that still blows my mind, like that it was like that hard to find.
Yeah.
That's just really cool.
Yeah, it's awesome.
It's worth saying twice.
Yeah, definitely.
Well, that would be the Banach-Tarski monster group.
Do you know the connection between the Golod-Safarevich theorem and how they get to here?
No. I like looked at the Wikipedia article a little because I was wondering what the Golod-Safarevich theorem was.
Because it's a statement of group cohomology, right? And
Yeah, it's a very much about like homological algebra over non-commutative rings. And what they get is that like this certain algebra you end up with is infinite dimensional. And I think from the infinite dimensionality of this specific algebra, you just get a counterexample of this, maybe by looking at like the units group or something. But I'm not sure exactly.
Just as a general comment, usually when I see someone's giving a food for thought talk on like Mauser thing, I get mildly worried that I'm gonna like understand nothing and just be overwhelmed by the first word in the talk. But it was very good, like simple throughout. Like that punchline at the end, like even I can appreciate how
awesome.
whack that is.
Excellent choices of shock value.
Yeah.
Actually, on that note, let us thank the speaker once more. All right.